All right, well, hello everybody. Thanks for coming. And yeah, ready to talk about some CS theory. Does anybody have any questions they want to ask about?
I suppose I can go first.
Great.
Last night I rewatched the 3 blue 1 brown video on the sliding block collision problem.
Oh yeah,
And
funny video.
yeah, it's a great video. So I have a sense of how to connect it to 5.1, but I'm having some difficulties getting everything worked out from the Grover move perspective. Particularly, I'm trying to identify some conserved quantities. So I know, for instance, that as we apply the Grover move over and over, if we square the quantities on each of these, like the points on the histograms, and we sum across them, we should get 1. So to me, that seems like a good conserved quantity, and maybe it's an analog for energy. But I'm having some more difficulty identifying the second conserved quantity that we can use to sort of tie everything together. I'm trying to do something where maybe we just sum across the magnitudes of the points, or maybe multiply by like the number of them, somehow sum across those, but nothing seems to work out. So I was hoping to get a little bit of assistance on that.
Sure. Yeah, I actually don't even know if you like really need to like watch that video per se to or follow that at all to like solve the problem. I believe it's also just possible to just, if I hadn't given you any hint, like maybe it would be easier. But I don't know. But let's just remember what's going on and see what occurs to us. So
Sure.
I'm imagining here, I guess, like n is little n is 4, so capital N is like 16. So yeah, let's just remember what's going on in Grover. So we have, well, like initially all these things, these bars, if you will. Yeah, as you said, their squares add up to 1. So if there's 16 of them, 16 times, well, I guess, okay, it's 1 for root 16 squared, that adds up to 1. So I guess they all start out, is what I'm trying to say, at like 1/4. And yeah, let's just remember what's happening. Let's say this one, this, I don't know, it's the magic 1. Well, maybe I can use the power of like copy paste here. Would that be amazing? Copy, paste. Ooh, look at that. Yeah, so like, let me erase these axes now. What happens? Like first, you negate this thing. Well, that's like -1/4. I guess the next step is like this reflection kind of across the average. Let's just figure it out just to understand what's going on. So we have like 15 things, so a value 1/4, plus 1 thing whose value is -1/4. I guess this adds up to 13 quarters.
Seems right to me.
Oh, but then we have to divide the 13 quarters. This is going to get gross, but well, let's just do it. 13 quarters is the sum. I guess the average is this over 16, so I don't know. So this means
13 over 64.
Yeah, so mu is like 13 over 64, which I suppose is like, 16 over 64 is 1/4. So this is, I don't know, maybe I'm making this up, but perhaps it's like 0.23 or something. So there's like this. Okay, and then we got some new values. And do this one more time. Paste. Yeah, so I guess then after we do that reflection kind of deal, these things will be all like a little bit less than 1/4. I'll probably figure it exactly out. And this one will pop up to somewhere in the neighborhood of 3/4, I guess. Okay, so and then we might repeat.
Mhm.
All right, so what are your thoughts? I mean, does this okay, I guess one question is like, should we try to like follow the hint or should we just try to think independent thoughts? We can go either way. I don't know.
Okay, so I've done a little bit of both directions. So
Okay.
if we want to try thinking independent thoughts,
Okay.
I've tried to formulate how our magic one
Yeah.
evolves with each Grover move,
Okay.
how all the non-magic ones evolve with each Grover move, and then how the average could evolve over each Grover move.
Okay, good.
So it seems like, well, here we could use the numbers of the fourths and the sixteenths and whatnot to get exact numerical answers. But I think more in general, it seems to me that when we have our magic one and then we like reflect it across the zero line, and then we reflect it again across the wherever the updated average is, I think it comes out to like the new average is something like the old average minus 2 times whatever the magic one is over big N.
Okay.
So it's getting smaller each time, or the average is getting smaller. The magic value is, oh, I have written down. Yeah, so the average decreases slightly, but our magic value increases by around twice the average.
Hold on. Let's actually do a little calculation here just to double check.
Okay.
Let's even like, I mean, let's do it. So okay, so these are all at I suppose we could write them at 16/64. And then if we're reflecting them like a mirror through 13/64, then you're 3/64 away from that mirror. So then when you go again, these guys will have, this new height will be at I guess 10/64. Does that seem right? And then this distance, truly, this was at like negative 16/64, and this height was 13/64. So you're actually 29/64 away. I mean, correct me if I'm wrong everywhere here. Away. So then if you go up another 29/64, you'll be at 42/64, I believe. I think this will be literally 42/64. So shall we calculate the new average?
Yes, let's do that.
Okay, so the new mu is, we have 15 copies of 10/64. We have 1 copy of 42/64. And if we add these up, we get 50, no wait, we got 150, 192/64. Then we're also going to be divided by 16. Does this factorize at all? What is 192 divided by 4? It's like 48. This is like 48. This is 3. It's also known as 3. So the new average is 3/16. Okay, which as you say is like 12/64. So indeed, this one, it went down a little. That's right. So for example, like, like one thing that doesn't change the average is, I guess, reflection through the mean, like part of the Grover step. Well, doesn't change the average. Right? But then things do change. Like, for example, when you like negate the special one, that certainly changes the average. It like makes it smaller.
I see, yes.
So, okay, good. So really, yeah, I mean, everything, I guess there's basically 2, well, I was gonna say there's like 2 mystery quantities at all the times. There's like the average, maybe the special things value, but really, I guess everything is real. There's really only like 1 mystery parameter that changes over time, because I mean, like once you know like one fact, like for example, the amplitude on the special string, then it does kind of determine all the other amplitudes.
Right, because we all know they're the same height and we have the sort of sum of squares equaling 1.
Yeah. So, Yeah, in principle, I guess that means that like, like in class, like, the like, okay, the amplitude on the special one, it starts out at like 1/√n, and then it goes to, in class, we basically said, okay, it goes to about like 3/√n, and then it goes to like about 5/√n, and then it goes to about 7/√n. These abouts are like slightly wrong. So I guess in principle, you could write down like literally kind of an exact formula for like how it makes these steps. It might not look super beautiful though. Like it involve like some square roots and stuff. Oh, there's something in the chat. Allow me to look at it.
I think it was a comment on the earlier arithmetic we were doing.
Oh, okay, thanks. Let me just get it out anyway. Oh yeah, thanks. Yeah, so we could do it. We could like write down this formula exactly. Might be fun. So for example, yeah, let's say this special amplitude, I don't know, I'll call it alpha. So if alpha is a special amplitude, then like what is the remaining amplitude? So I guess we know that like alpha squared plus n minus 1, like if beta is the other one, beta squared is 1. So that means if you think of like alpha as like a known quantity, then like this is like beta squared is 1 minus alpha squared over n minus 1. So like beta is, I guess, square root 1 minus alpha squared over n minus 1. And then, yeah, it's starting to look like not super enjoyable. Like,
no.
like I guess you'd be like, all right, well then like the mean is then alpha plus n minus 1 times this beta over n. It's not too bad, like alpha plus, okay, if I multiply this by, so I get like root n minus 1, root 1 minus alpha squared over n. Yeah. Yeah, and then you're like, oh, okay. One thing I can say, like, there's a couple things we can say. This is like a weird advice, but like I'll pop it up just because it comes to mind. And actually, I'm pretty sure what I'm about to say is like super relevant for this problem, but like I'm not just, blurting out the answer. Like I'm just like staring at like some weird expressions. If you ever see like in your life like this, like square root of 1 minus alpha squared, this looks kind of gross, but if you like reparameterize, it can become potentially better. What I mean to say is like, does it remind you of anything at all? Like the phrase square root of 1 minus alpha squared?
Reminds me of some sort of trigonometric or hyperbolic thing.
Very good. Yeah, exactly. Oh. And maybe you wouldn't be so surprised.
Yeah. There should be pi floating around somewhere, which means trigonometry isn't that far behind.
Exactly, as 3 blue 1 brown does say, you should look for a circle. Whenever I see like, this is like an automatic life move. If I ever see like 1 minus alpha squared, I think to myself, maybe I should write alpha equals either sine theta or cos theta. I'm not sure which one. Let's say just say, I don't know, sine theta. Because at first you're like, that makes things worse. Like now alpha just used to be alpha, but now it's sine theta. But it makes this better because this is now 1 minus sine theta squared square root.
And wow, that's cosine squared.
Yeah, it's cosine, it's square root of cosine squared theta. So it's, well, I guess it's either, I guess it's positive cosine theta. And so you're like, oh, well, that's sort of better. Like it's a little bit more symmetrical. Like this was actually what we were calling beta, right? So like this beta is now cosine theta over root n minus 1. Okay, that's beta. And like alpha was sine theta. So, okay, it's not so clear that this is like helpful, but maybe it's helpful because, I mean, I guess, yeah.
I mean, this is certainly a new idea that I will need to play with, but I think that
That's very tempting to like, go ahead.
yeah, just drawing a circle. Like, so something from the video implies that maybe we are tracing some arcs around the circle, and we can say something about theta as it grows or as it traces out segments of the circle.
Yeah, for example, I guess this is like saying that like, okay, like in general, you know, at some time, like the amplitude on the special string, we were calling it alpha before, maybe we should call it sine theta. That's, okay, if this is theta, sine is, which one? I guess it's this blue height. And cos theta is, well, this, although the other ones, they're all cos theta over root n minus 1. So, okay, then like what happens? Like one thing that happens is you do this operation of like negating the coefficient, the amplitude on the special one. So that like has like a reasonable geometric picture. I mean, it just like if you think of at a moment in time being parameterized by maybe neither alpha nor beta, but like parameterizing it by theta, then this like Grover, this part of the reflection is kind of simple. It like kind of switches theta to minus theta, like it flops you down to here. Now we still have the problem that we've kind of like stalled a lot from like investigating that other move, the one where you like reflect everything across the mean. And so I guess when you do that, like if you're sitting at, you know, sine theta is the special amplitude, and like all the others are cos theta over root n minus 1. Then, okay, when you do this like reflection through the mean thing, I guess you'll get to a new theta prime situation where you're like holding on to sine theta prime and like cosine theta prime over root n minus 1. And it would be pleasant if like theta prime like bore some nice resemblance or relationship to theta. And it's not so clear. I mean, how easy is it going to be? So like, okay, like the mean, I guess, is sine theta plus you have n minus 1 copies of this. So like root n minus 1 cos theta over n. Yeah, it's not amazing. So then like the sine of sine, like your distance of like the special amplitude from the average is like sine theta minus this thing, sine theta plus root n minus 1 cos theta over n. Like, okay, I don't know, I could put an n here. Well, I guess you get like n minus 1 sine theta plus root n minus 1 cos theta over n. And if that's your distance from the average, then like your new value is like your old value plus twice this distance. So you go from like sine theta goes to like sine theta plus 2 times this. Maybe I'm doing it backwards. Okay, if this is sine theta, what did we just do? We subtracted sine theta. Okay, so maybe probably minus 2 times this. I don't know, I'm mixing up my things. So you get like 2 sine. I mean, you'll get, oh, so that's n sine theta minus over n minus 2 times the above. So you get like, how many sine thetas will you get? You'll get like n minus 2 and minus 1 sine thetas, which is
really close to just 2 sine theta, but then there's this additional cosine stuff floating around.
yeah. Well, wait a minute. Oh yeah, it's 2 minus, and I might have botched something up here. Well, okay. You can
like I can do the arithmetic, but I think
yeah.
I'm satisfied with this injection of the sine theta idea.
Yeah.
I want to play around with it. So I guess, if other people have questions, like definitely let them.
Okay, yeah, fair enough. Like that's one new idea at least that might help out. And yeah, we can come back to it, but we can also put it on pause for now.
Sure.
And, yeah, is there any other question that somebody wants to offer up?
I would be interested in looking at 2 or 3. So if
2?
anyone has any preference for either of those, then
2 or 3. Yeah, those are the other 2.
yeah, I guess that's
I
mean, if
which
no
one?
one's saying anything, we can just go for 3, I guess.
3. Okay. What is going on in 3? Oh, we're going to try to prove a slightly weaker version of the Schwartz-Zippel lemma. Okay. What are your thoughts on 3 so far?
Well, so yeah, I was trying to use the hint.
Okay.
Also, just a note, I think I don't think it says that Q is prime, but I assume it is, right, for it to be a field. So
It need not be a prime. It has to be a prime power.
oh, prime power, yeah.
Yeah.
Yeah, I guess I was just trying to use the hint. I took care of the first part, which just
First part
follows
meaning
from
like this
the
bit?
explain, yeah, because that just, I guess, follows from what we did in class.
Okay. What about this one?
Is
that
yeah,
part
I
okay?
also
Or?
did that. I'm trying to remember exactly why I knew it was the
Okay.
case. Yeah, I mean, if you want to go over it, we can, but I remember working it out and it made sense.
Okay, so let's assume that's fine.
Yeah. Yeah, so this line stuff is
The line stuff, yeah.
So one quick question before we actually like jump into it is for a line to pass through a point, does it just mean that like that set contains that point?
Yeah.
Okay.
Yeah, actually, I mean, it's funny. I was talking about this in class yesterday. I mean, there's a lot of analogies between, okay, so I mean, we are looking at, vector spaces over a finite field. And there's like a lot of analogies between them and like vector spaces over, let's say, the real numbers, which we're all used to. But you always have to be like mildly careful. I mean, these are like, yeah, you always have to like think about them. They're always inspiring, but you also have to be careful. So for example, like we could have, I mean, maybe this is probably going to end badly, but like we could imagine drawing a picture. Let's take Q to be 3.
So I was just doing it in 3 and then 2 dimensions.
2 dimensions. Okay, that's good. So that's like n is 2. So when Q is 3, it's a prime. So it's kind of convenient because then the field FQ is, just the numbers mod 3. That's nice since it's not a prime power. So like you can kind of like imagine well, this is I mean the set F3 squared. It can be like, all right, this is 0, 0, 1, 0, 2, 0. What do I have to do here? 0, 1, 0, 2, 1, 1. Should zoom in. Like 2, 1, 2, 2, and 1, 2. And like what is like a line? So like it's weird. Like you you pretend you're like in 6th grade, but like everything's like a little bit askew. So you're like, okay, well, in a line, you have like a point and like a slope kind of. So, I mean, a line in general is like you have like a base point and like a vector in the direction of a line. And like the real numbers, like if this point is called, I don't know, like x, and this vector is called, I don't know, v vector. I guess x is also a vector, but then like the line is sort of like all the points x plus like t times v vector, where t is like a real number. It's like, oh, this is like your new, it's like an infinite line. This is t equals 0, and like, I guess this is t equals 1, and like, it extends indefinitely. And it's like the same story, in finite fields, except, well, there's only like 3 in this case values for t. So for example, like the line, let's say through, I don't know, like 0, 1 in the direction, I don't know, 2, 0, I don't know, it's like, all right, you start at 0, 1, that's in the line. And then like you add 2, 0. So that's, I guess, oh, let me make this 2, 1. So it'll be like more interesting. You add like 2, 1. So you're like, all right, 1, 2, 1. So it's like, this is the next point in the line. Kind of going in this direction, sort of, but then like it wraps around. So like you're adding like 2, 1 again. So it's like 1, 2 goes here. And then that's actually sort of it. Like kind of it wraps around. So I mean, like it's sort of a weird line that's like doing this and like coming back here. And yeah, there's only 3 points on it. So that's a line. And
yeah, so I guess that gives us some stuff to work with for the counting part, which is
sure
stuck on.
Yeah, how many lines pass through alpha? Well, let's just finish it here. I mean, okay, wait. How many lines pass through alpha? So let's say this one is our alpha. So how many lines do pass through it? Like here's another line through it. You can take the line through it in direction, let's say 1. Just for kicks, I'll call it 1 minus 1, although that's actually like 1, 2. But like 1 minus 1. So like we start here, and then we go over 1 and down 1. That takes us here. And we go like over 1 and down 1, whoop, and get back here. So it's kind of like, this is our line. Comes down here, comes through here, and comes through here. And that's like another line. This diagram is getting to be a mess. Did we get the exact same set of points?
Yeah, that's pretty interesting. The -1 thing I hadn't thought of, because that makes, I guess, it a little more clear what we're looking for. Like certainly anything that starts on the point will work, but then we can also just take any other point and just direct it straight to that point.
Yeah. So I think one thing that happened here is, you see, let's go back in our world of analogies, like in like, I don't know, R2, we could start this point like, I don't know, 0, 1. That's like 0, 1. You could take the line in direction, I don't know, let's say take the line in direction 1, 1 again. Now it like literally looks like, sorry, in the direction 1 minus 1 again. So like it literally looks like this. This is the line in direction 1 minus 1. But I think the analogy of like what happened up before, which is like a little bit weird, is like you could also say like, let me look at the line in direction 5 minus 5. And then you might be like, oh, wait a minute, I'm like weirdly, so like that's like 1 minus 1. And then of course like 5 minus 5 is like here. So you might say like, oh, surprising, like these are actually the same line, even though 1, 1 and 5 minus 5 are different. Well, of course, we're not too surprised. We're like, yeah, that's how, I don't know, parallel lines work or scalar multiples work. But I guess that's exactly what happened here too, because weirdly, you know, same thing, like this, I guess, is a scalar multiple of this. Like this one is like 2 times this one. Mod 3. So all like, pictures aside, like, these 2 lines I genuinely kind of randomly picked them, they're like happen to be parallel lines. Like because like the direction you're going was like one direction was like a scalar multiple of the other direction. Does that make sense?
Yeah. So I guess maybe what I was just thinking is that we could use any point and just it would work. But I guess any or for the starting point. I'm thinking now.
Yeah, you can use any point for the starting point. And I guess, well, one thing you have to ask yourself is like, how many? Okay, this has like this line, this self-same line, like we drew this like blue dashed thing and yellow dashed thing, but like actually they're the same line because the line is really just defined by like the set of points.
Sure, yeah.
So for example, like another similar line, or well, another line is we could go, let's say in this direction, we get like this point, and this point. And that's like a line. And like a parallel copy of that line is if we went like 2 steps and then like another 2 steps and then like another 2 steps would also take us here.
Yeah, so it's actually like pretty difficult to count this.
Yeah. But I think it's true. Well, okay, I know it's true that 2 points always determine a line. I mean, this is like a general phenomenon in R2. If you put 2 points, and in any dimension like R3, also 2 points determine a line. And I guess this phenomenon is actually going to also hold over the finite fields.
Yeah, and so we need one to be the point that we're interested in. And then I guess we just need to pick the other so that we won't run into the situation that you just drew where like we consider both of those points on the parallel line.
Yeah, that's true. Actually, if we like, let's make this picture a little bit less disgusting or like repeat it over here. We could try to look at like quote unquote all the lines. I don't know why I said quote unquote. We could try to look at all the lines like through this yellow point, this yellow point. So one we talked about, the first one was like, it included this one and this one and this point. So like this bizarre thing was a line. And then we saw this line that had like this point, and this point. That was a line. What other lines do we have? We have like some vertical lines. Like, I don't know, this point, this point. That's a vertical line. And let's go over here. I guess if you go like up and to the right, you get here. You go up and to the right, you get here. So I guess like this one is also a line. I mean, okay, I don't want to draw it. That's also a line. And yeah, so I think like there's like exactly, I think, now we could try to find and see if there's like other lines, right? So like, I don't know, like, well, but I guess there won't be, right? Because like if you start this yellow point, if you believe that any 2 points define a line, then like you can pick your favorite other point, like, I don't know, this one, but then you're like, oh, I already have the black line that goes through them. So like, yeah, so probably this is like all the lines.
The way that the black one is drawn, it looks like it's crossing the others, but like, it's kind of going off to the top and then coming back around on the right. So we basically just covered the whole entire thing.
Yeah, to be honest, there's like no real natural way to draw like the liney part of the line. Like really at the end of the day in these finite fields, you just like a line is like a subset of the points. And so like, arguably maybe the best way to draw like the black line is you're just like, well, it's this point, and this point. And like, you don't try to like encircle it or like draw a line through them. But still, I mean, I don't know, at the same time, you like want to hang on to some of your intuitions from like the regular geometry of the real numbers.
That makes
but
sense.
I think some of these phenomena will persist in higher dimensions too. So for example, like if Q is 2, like not only do the opposite, like Q is 2 and N is 3. So if the number is mod 2 in like 3 dimensions, I'm just going to draw this thing. I don't know if you can tell. Like here, every line I think has like only 2 points on it. And maybe like every pair of points constitutes a quote unquote line.
Yeah, that's interesting. That's like a much better way to think about it, because I was kind of going algebraic and yeah.
Well, you need a mix. Yeah, like you want to
Yeah.
like retain like some intuition of geometry, but there's only so much geometry in the finite field, so you also have to like do some
Yeah, like when you go to actually prove it, you'll need to, to do
yeah.
Okay, cool.
Okay, let's pause a little bit there, and we can come back to any of these problems if we like. But is there another question?
I mean, I wouldn't mind looking at 2, but I want to give everyone a chance to ask questions if.
I have a question about what sort of mathematical machinery or just facts we can carry around without proof in these problems on modular polynomial arithmetic. Like, for instance, do we know, like, does distribution hold in modular polynomial arithmetic? Like polynomials alpha times the quantity beta plus gamma is equivalent to alpha beta plus alpha gamma.
Oh, for polynomials?
Yeah.
Like P of X times like Q of X plus R of X.
Yeah, mod.
Oh, right, like mod with the coefficients like mod.
Like some degree D.
Yeah, you could even say like, well, coefficients we always like to typically assume are in a field. So I might not even say mod per se, but well, we can ask about like this. Basically, I mean, you can assume things. For example, like I would just say, yes, this is true. It's true that like, okay, like I didn't like exactly, for example, define multiplication of polynomials over a field. I just kind of took it for granted that the definition was clear. And I mean, I understand you bringing it up because like, okay, like particular, like this thing on the homework is like kind of confusing. Like you could easily ask like, well, what do you want me to like prove per se here? And for this particular question, like I said, you can be very brief. Maybe it's almost like just, you know, make sure you understand, you can rephrase it as make sure you understand why like this can be viewed as a vector space over of dimension L over this scalar field.
Yeah, because I was sketching out like what I would write if I were to go about and prove it. And it's like, oh, well, this proof works if I have this fact. It's like, okay, do I need to go prove that this mechanism works? And then I wrote a little sketch for that mechanism. Like, okay, eventually we have to get down to a fact where we can just sort of say, yes, this is right. Like if I have, like, I think the base fact that I can always have is that if we are taking just mod a normal field, like if we have a number and like 8 mod 3, then, you know, we can split that number into a multiple of the modular thing plus a remainder, and we'll eventually get down to the remainder.
Yeah, I guess Yeah, that's even like overboard for me. I used to have the word like, very briefly in here, and I like deleted it, but like maybe I should have left it in there. I mean, I guess what I'm saying is, well, one thing is like, I'm kind of like, take it for granted. I want you to like take it for granted that, I mean, we already discussed it, like, okay, that's a bad color. Like, FP, the numbers mod P is a field. I can't write. FP is a field. And so particularly like all the rules of arithmetic, like definitely you take them for granted, like addition is like associative and commutative, and so is multiplication, it has distribution. I mean, this is the nature of a field. And I'm even like kind of assuming like all throughout this that like, it's taken for granted that like, we know what it means by like this vector space FP to the n, and that this is a vector space, and like the usual laws apply. And of course, if you have any like question about it, like feel free to ask. But I guess the thing that like I just want to make sure you think about and is that so in class we I sort of defined these fields modulo like a prime power in terms of polynomials, a little bit informally. I mean, I said, for example, like I mentioned that like, let's do a specific example, like F9 is F3 squared. First I said, oh, you can think of it as like all the expressions that are like A plus BI, or like A and B are mod 3. And like I took it for granted that there's like the traditional rules for like how to like manipulate these numbers. And then a bit later we said like, oh, you can also say it's basically the same thing, but it's like, oh, it's all polynomials A plus BX, where like A and B are numbers mod 3, and like it's like mod this irreducible x squared minus 1, which basically just means like this is like formally 0. So like x squared is formally 1. Like whenever you see an x squared, you can replace it by the number 1, which is exactly the deal with I. Oh, sorry, minus 1. This should be mod x squared plus 1. X squared is minus 1. Whenever you see an I squared, you can just formally replace it by minus 1. And I guess like I just wanted you to think a little bit about like, well, actually in either of these two phrasings, like it doesn't immediately look like a vector space where you have like, let's say, column vectors. So what's up with that? Perhaps it's not. So actually, I thought of like one or two ways in which you would answer this acceptably. Like either you might say like, well, these objects that we're manipulating, like we can like have a mapping of them onto vectors in like a natural way, like vectors in like F3 squared of like, vectors with two numbers that are mod 3. It's not much of a secret how you would do this. And then you just want to like check that like the like usual rules for manipulating these field elements or polynomials are like the same as the ones for vectors. And really, we're only talking here, there's no notion of multiplication per se for vectors. We're really only talking about scalar multiplication and addition.
Right, yeah, so I had written out a proof sketch where it's like, oh, all I have to do is show this scalar multiplication and addition, but I'm like, okay, so I could stop here, or I could go another level. So yeah, I think I have a good sense of how much machinery I can carry around. I just wanted to ask. Yeah, frankly, like, I just want like one or two sentences saying like, yeah, scalar multiplication and addition are fine. Or if you're like a math, lover, you could be like, well, what does it mean to be an abstract vector space of our dimension? It's like a set that supports, all these operations of addition. It's closed under addition and like scalar multiplication. And so you don't have to literally mention like column vectors per se if you're like really gonna be like hardcore math about it. You can just say like, yes, these objects supports, a notion of addition and scalar multiplication. But yeah, maybe you got it. I've said too much.
Yeah, so this I just wanted to make sure that you all were in the right frame of mind for the subsequent questions. Because yeah, I mean, it's a little bit funny, like it's asking you to think about, like sometimes we think about like FQ as just like a set of numbers, like we forget a little bit about like, oh, how do we get these numbers? I mean, when it's the numbers like mod or prime P, they're just, that's fine. But you know, this finite field is a bit funny. And you know, it's connected with like how you would actually on your literal computer like implement these numbers and literally implement like multiplication of two field elements. Is there another question?
Yeah, I guess I had a question about part B.
B, okay.
Well, I guess I kind of need to say some of what I did for part A for part B.
That's fine.
Or yeah, so I mean, I was trying to just stick them into vectors.
Yeah, that's fine. Yeah.
The polynomials, and then the basis comes like pretty clear. But yeah, I guess I'm slightly confused with how the modular polynomial arithmetic works, because yeah, I guess I have to say what my vector representation was. So
that's fine. Yeah.
So, yeah, I was just putting like the
coefficients into a vector.
Well, yeah, I was actually putting in the x's as well.
Okay, yeah, you can do that, but I guess
because then the basis would be like yeah, you can form the basis. That's the only way that I can.
Well, actually, that doesn't quite make sense now that I think about it, because, well, I guess when I say, when you see a phrase like a vector space of dimension L over a scalar field FP, you know, vector space of dimension L over a field, you know, like the simple way to think about that is like, okay, like the objects here are column vectors of length L, and you know, about L entries, and then each of these entries is supposed to be a number from the field.
Yeah, so I guess okay, we can.
And I guess like X is just like a symbol, so it's not really a number from the field.
Yeah, that might make things easier, I guess, because yeah, I had X's in there and it was getting kind of confusing. I guess I could still ask one of the questions that I was running into though, which is like, if I have something of okay, so R of X here is degree L. So if I have something of degree like bigger than L,
yeah,
then when I mod it by R of X, we know that we decrease the degree by L, right?
But, you even like decrease the degree to something that's less than L.
Oh yeah, like so, but the degree is what it was minus L, or that's not always true?
Sort of, right? In the sense that like
mod L, sorry.
Like, you know, when you're doing numbers like mod 10, you see like 543, that's but you want to say like mod 10, that's kind of like saying like, okay, like all 10s count as 0. So you could be like, oh, so I could like subtract 10 from this and get 533, and like these are just treated as equal now. And you could say, you know what, I'm going to actually subtract like 50 times 10. So 50 times 10 is like also considered to be 0. If I subtract 50 times 10, then I get like 33. And you're like, oh, I'm going to also subtract like 3 times 10. And then you'll get down to 3. Wait, where did the, yeah, okay. And then you're like, okay, there's like no more, it's not really anymore like effective to like subtract multiples of 10. Like I've kind of got down to the smallest thing I can get down to. So like maybe this is where I'll stop.
And so that's how the degrees work when we're.
Yeah, so like more generally, let's say we're like, I don't know if I know like a good, think like, let's say P of X is X cubed plus x plus 1. And we're going like modulo 3. So then, I don't know, we might have like two polynomials like 2, terrible color, like 2x squared plus 1 times x squared plus, well, we could even say like x to the like 5 plus x plus 1. And then like mod p of x. Okay, first we multiply this out like normal. So we get like 2x to the 7 plus 2x cubed plus 2x squared plus x to the 5 plus x plus 1. And they're like, okay, now we have to like mod out by this thing, x cubed plus x plus 1. So it's really like actually like, you can either like do it like mentally, like, all right, what would be like a good multiple of like x cubed plus x plus 1 to subtract out? And you could say, oh, maybe I should subtract out, like subtract, you know, looking at this like biggest thing, which we're trying to get rid of, like 2x to the 4th times x cubed plus x plus 1. Like since, you know, this is supposed to count as 0, that means this whole thing is like also counts as 0. And it's like nice, if I subtract this out, then I'm subtracting 2x7 minus 2x fifth minus 2. I'm like doing this minus this. And I guess that gives me, okay, the highest power is x to the 5th minus this. So actually I get like 3x to the 5th from here. And then plus 2x cubed plus 2x squared plus x. And then 1 minus minus 2 is plus 3. I'm also like all along, I'm also going mod 3. Like this is like, oh, cool, like that's 0, that's 0. And so I got down to like 2x cubed plus 2x squared plus x. Then I'm still not done because I'm like, oh, but like, you know, I've still got x cubed plus x plus 1 is 0. And like, it would be like effective to like subtract off another multiple of that. So I'm going to subtract off, like looking at this top term, I'll subtract off 2 copies of x cubed plus x plus 1. And I'll get something that's still congruent to the original thing, like equivalent to the original thing. And I guess I'll get 2x squared. I'll get x minus 2x, so like minus x minus 2. If I do this mod 3, I might be making some arithmetic errors here, but 2x, oops, wait a minute. No, that went away. That's just 2x squared. I'll get like 2x squared plus 2x plus 1 or something, mod 3. And this is where I stop because I'm like, all right, I mean, I did the coefficients mod 3 all along, but like, there's no longer like any like effective multiple of my p of x cubed plus x plus 1, that I could like subtract from this to like make it smaller, meaning of smaller degree. Because like, you know, any multiple of x cubed plus x plus 1, it's gonna have like a top term that's at least x cubed. And I already got this thing's degree like below x cubed. So this is where I'll stop. And this is where you will like stop. And you kind of see that like, again, with like modular arithmetic of numbers, you know, if you have like some like big polynomial, like high degree polynomial, like mod this x cubed plus x plus 1, you know, like keep subtracting stuff off until like this thing has degree less than 3 strictly.
Okay, yeah, and so I guess, but we don't really know. All we know is that that's the degree, or the bound on the degree, but we don't really know what's going on with the lower order terms.
Not really, yeah.
Yeah.
I mean,
because that's the issue that I'm running into when I'm trying to put the stuff in a matrix.
let's even just look at that problem, and maybe we'll do like an example of that problem. Let's see, where were we? Somehow I'm naming everything alpha today. So fix a particular alpha and consider the function m sub alpha, which is like multiplication by alpha, verifies the linear transformation and hence representable as a matrix. So yeah, like let's try to do an example here. The idea there. Let's go back to F9. So here like P is 3 and like L is 2, and like the irreducible polynomial or the prime polynomial is like x squared plus 1. This is the thing that we're treating as like formally 0. It's kind of like saying x squared is treated as -1, which is, some people would prefer to call x I, but we can just also call it x. So we need to pick like our favorite, well, a particular value in this field, alpha, to consider multiplication by. I don't know, let's do alpha to be 2 plus, I was gonna say 2 plus I, but we can say 2 plus x, either way. So we want to understand why the operation of like m sub, what's called m sub alpha, or like this operation, or the more expansively like multiply by 2 plus x operation, is actually like a linear transformation in the vector space point of view. So, a generic element of F9 is, a plus b x, or a plus bi, where these are like mod 3. And how do we multiply this by alpha? We call this like, I don't know, beta. So on one hand, right, from the previous part, we're also sort of in the back of our minds thinking of beta as a vector, like a, b. But we also think of it as like a field element. So how do you multiply 2 plus x, like alpha beta times beta is 2 plus x times a plus bx. So how does it work? You're like, okay, I'll expand this out. I get like 2a plus 2bx plus ax plus, okay, now we get like bx squared, and x is like I, it's -1. So we're like, okay, this is like 2a minus 1 plus, and then we can like a plus 2bx. Or if you want to go like mod 3, this is like 2a plus 2 plus a plus 2b. Okay, did I make any mistake here? Okay. So this, if we think about this as like a vector, it's like 2a plus 2, a plus 2b. And so like the transformation that took generic element beta to like alpha times beta is kind of like in the vector world, it like took this vector ab to like this vector 2a plus 2, a plus 2b.
Is there
Actually,
a
what's like
b?
Pardon me?
Isn't it 2a minus b?
I hope so, because like
it's
there's something
b,
that's like really wrong
yeah.
about this. So I'm like really hoping there is a bug somewhere.
Because it's plus bx squared, and you're plus x squared.
Oh
like
yeah, I don't know why
1.
this. Oh, I forgot this b. Thank God, because I was like, I don't know what's going wrong. Like there was something wrong. This is not a linear transformation. It's like an affine transformation. But yeah, thank you. Like I made a mistake here. I dropped this b, so this is not -1. It's like minus b, or you might also call that plus 2b. So this should have been 2b. Thank God. So yeah, like what has happened is like it's kind of like what we sort of saw is that like the like vector representation of like alpha times beta is sort of like we took the vector representation of beta, which was this, and well, it turned into this. And like the idea is that like this is some matrix multiply of this. I guess it's like this is like, let's see if I can figure it out on the spot. A, B, I guess it's like 2, 2, 1, 2, perhaps. Like this matrix times AB is indeed this. So yeah, we sort of saw this 2, 2, 1, 2. When this alpha happened to be whatever example we use, 2 plus x. So we kind of saw it like this in the end, like, okay, if you want to know if you're really obsessed with, this particular field element, 2 plus x, you really want to know, like, hey, if I got the vector representation of some element beta, and I wish I had the vector representation of this element, like 2 plus x times beta, how could I get it? Well, luckily, it's like you do like a matrix vector multiply. You multiply this matrix against this vector, and you get the result. So I guess a little bit, the question is asking you, like, make sure this like always happens, like for every value of alpha in like every field. So in some sense, like it's kind of maybe on your computer, you would like have some kind of like mapping between like, if this is your name for alpha 2 plus x, you'd like have some table where you're like, well, I'm gonna also remember this matrix, because like if I ever want to like multiply by this, I could do it. One way I could do it is like, I could do it in exactly this way, but like it might be more effective to just like do a matrix multiply.
What was alpha again? I'm just trying to see if it lines up with like what
alpha was like this, just like I took like
2 plus x,
like a random example, 2 plus x.
Yeah, I'm just trying to see if that like the matrix we got lines up with what I was trying.
Yeah, there's a question, like there's something is, I don't know, going on with these entries and like these entries. But I guess really what this question is asking you is to make sure, or to prove that like, maybe this always happens, that like if you look at, if we're now like, oh, like what's the vector representation of, I don't know, I'll pick another random element, like, I don't know, 1 plus 2x times beta. Is this like a matrix multiply times the vector representation of beta? Or maybe it's not, like maybe it's not even a linear function. Like maybe if this is like a, b, maybe this answer is, a squared plus 1b, like something which is not like a linear transformation. But it's not, it is a linear transformation. But this is what you have to like reason about.
Yeah, that makes sense. So what I was trying to do is approach it with like just giving a matrix that captures this, but are you saying it might be, or well, I guess that's probably what the final answer will be, but you're saying we could also like just multiply it out and then show that came from a matrix?
Yeah, I think in this, you may or may not find, I'm not sure, but you may or may not find that it's easier to argue that a matrix exists than to like sort of really say immediately what the matrix is.
Okay.
I don't know if that's true or not, but like, I guess the way the thing is actually phrased is kind of phrased in like a bit of like a abstract linear algebra way, like like if you remember like all the way back to linear algebra, like abstract linear algebra, like they're always careful to like first define like theoretically the notion of a linear map or a linear transformation, and then they're also like, oh, you can, for every linear transformation, like you can represent it like concretely as a matrix multiplication, and conversely every matrix multiplication corresponds to like an abstract linear transformation. And like all this is true. Sometimes it's good to remember. Sometimes you're just like, chill out, math. Like we all are kind of fine with like conflating the notion of like a matrix multiply and a linear transformation.
So I guess I didn't even know that was, because I just thought linear transformations were more general. So the reason I was going straight for the matrix is because I thought that would be how we show that it's representable by not that the fact that it's a linear transformation would imply that, but
yeah, I guess even the next question is like how to actually compute this matrix. So in fact, in some sense, like
yeah, you kind of have
if you show C, then you're like, hey, this sort of shows B. Like if I just explain to you like why this is like a matrix multiply, then a matrix multiply is a linear transformation. I guess like if you're into abstract linear algebra, like you could view this as like a bit of a more like natural progression where like in B, you don't even like talk about matrices per se. Like you could be like, well, abstract linear algebra, like a linear transformation is, just like a map, like L that maps, like vectors to vectors. and has the property that like L of x plus y equals L of x plus L of y, and I guess like L of like C times x is like C times L of x. Like that's the definition of like linear transformation. And like it might be, in fact, I'm sure it is easier to verify that the sort of operation L of like multiplying by a field element like 2 plus x or any field element just satisfies these little rules for what a linear transformation is. And then you could say like, oh, therefore by like my knowledge of linear algebra, I know automatically that there should be a matrix representation for this transformation. And then you would like find that matrix in C. But if you were like the kind of person that was like not that into abstract linear algebra, you could just be like, whatever, like I'll just directly solve C, and that shows that it's a linear transformation.
Cool. Yeah, that's a cool fact. I did not know that you could represent every single linear transformation as a matrix. So.
Yeah, it's cool. It also explains like why the rule for matrix multiplication is what it is. So like if you never thought about that too deeply before, it's good to think about.
Yeah, I mean, does that only hold when it's finite? Or I guess we could have like a
When it's finite dimensional.
okay.
Yeah, you can have like infinite dimensional vector spaces. We won't really in the course. And then I guess it's not too nice to define infinite matrices. So it's probably best to say, yeah.
Okay, cool. Thanks.
Yeah. Say, I guess it's almost well, time is sort of up, but if there's like a very short question I can answer. No. Okay.